A regular computer bit is either a 0 or a 1. A qubit can be something stranger than both at the same time. Every piece of information your phone or laptop handles comes down to bits. A bit is like a light switch. It is either off, which we call 0, or on, which we call 1. That is the whole foundation of classical computing. A qubit is also a unit of information, but it follows the rules of quantum mechanics instead of everyday physics. Those rules are genuinely weird, and that weirdness turns out to be useful. The big idea is called superposition. Before you measure a qubit, it does not have to be just 0 or just 1. It can exist in a mix of both states at the same time. Think about spinning a coin on a table. While it is spinning, it is not heads and it is not tails. It is genuinely in between. The moment it lands, you get a definite answer. A qubit behaves a lot like that coin, except the physics behind it is real and precise, not just a metaphor. What makes superposition more than a party trick is that you can do calculations on the qubit while it is still in that mixed state. You are essentially working on 0 and 1 at the same time, which lets certain problems be attacked from many angles simultaneously. There is a second quantum property called entanglement. When two qubits are entangled, measuring one instantly tells you something about the other, no matter how far apart they are. This is not about sending signals faster than light. It is about a deep correlation baked into the physics. A third property is interference. Quantum algorithms are cleverly designed so that wrong answers cancel each other out, like waves colliding, while right answers reinforce each other. That is how a quantum computer steers toward a useful result. Here is where it gets practical. Qubits are incredibly fragile. Any stray vibration, heat, or electromagnetic noise can knock them out of superposition, a problem called decoherence. This is one of the central engineering challenges researchers are working on right now. To fight decoherence, most quantum computers today operate near absolute zero, colder than outer space. The chips themselves are tiny, but the cooling hardware around them can fill a whole room. It is also worth being honest about what quantum computers are not. They are not faster at everything. Browsing the web or playing a video game on one would give you no advantage at all. They are specialized tools built for specific types of hard problems. The kinds of problems where qubits could genuinely help include simulating molecules for drug discovery, optimizing complex logistics networks, and cracking certain encryption methods, though that last one is still far off, and researchers are already building defenses against it. So a qubit is not just a bit that works harder. It operates under a completely different set of rules. And those rules open up possibilities that classical computers cannot easily reach, at least not in a reasonable amount of time. The field is still young. Researchers are building bigger, more stable quantum systems, but there is a lot of ground left to cover before quantum computing becomes a widespread tool. What we have now is genuinely promising and genuinely hard. If you want to go deeper, the concept of quantum error correction is where a lot of the real action is right now. It is worth looking into.